Hess's law gave us one way where we could use known thermochemical equations to figure out the enthalpy change associated with a new chemical reaction. But there are so many possible chemical reactions out there that just taking all our known thermochemical equations doesn't give us enough information that would allow us to predict an enthalpy under standard state conditions for every chemical reaction out there. But Hess's law actually implies something even more powerful, which we can use to come up with good enthalpy change values for unknown reactions. And the tools we use to do that are what are known as standard heats of formation. Because enthalpy is a state function, we can use heats of formation values, or what we call delta H naught F values, to calculate enthalpy changes for reactions that we've never seen before. Standard heats of formation are an extension of what Hess's law implies, which is to say that we can figure out through careful calorimetry experiments how much heat will be absorbed or released making a specific chemical from the elemental form of the atoms that make it up. And then, by invoking Hess's law, if we know the difference in the enthalpies of formation between the products and the reactants, we can figure out the enthalpy change for the overall reaction. And we have enough calorimetry data that we can actually catalog the heats of formation, or what we call the delta H naught Fs, for pretty much every chemical in every phase that we might be interested in. So what is a heat of formation? Well, a heat of formation is a specific enthalpy change for the synthesis of 1 mole of a particular chemical from its constituent elements in their standard states. So essentially, an enthalpy of formation is, I want to make 1 mole of methane in the gas phase. Gas phase methane is the standard state of methane at 1 atmosphere of pressure and 25 degrees Celsius. I am going to write a chemical reaction in which I make the methane from solid carbon, the elemental form of carbon, and 2 moles of hydrogen gas, the elemental form of hydrogen. So the elemental form of carbon is simply solid carbon. The elemental form of hydrogen is a diatomic gas, H2. If I take 1 mole of this and I take 2 moles of that, I can make 1 mole of methane. By comparing the heat released in different chemical reactions related to the synthesis of methane, I can figure out an enthalpy value for this chemical reaction under standard state conditions using Hess's law. And the key is you don't have to figure out that enthalpy change value. It's already been done through experimentation and someone has put it in the table. So the enthalpy change for this reaction is what we call a heat of formation, or a delta H naught F. For methane, the delta H naught F is negative 74.8 kilojoules per mole of methane. And this is really powerful because now we can use Hess's law without writing out all the reactions. We can say, I know how much heat needs to be released to make methane from carbon and hydrogen. If methane is participating in a chemical reaction, I now essentially know an enthalpy value for methane in the gas phase. And what I can do then as an extension of Hess's law is look up the heats of formation for all the chemicals that are participating in my chemical reaction. So this is very much like doing Hess's law without having to write out all the relevant chemical reactions and putting them in order to figure out the enthalpy change for your overall reaction. Instead, we're writing simple chemical equations describing the formation of each chemical participating in a chemical reaction. And we're saying how much heat is gained or released when we make this specific chemical. Note that the enthalpy of formation for any element or elemental form is 0. So if you're talking about solid carbon, the enthalpy of formation for solid carbon is 0 kilojoules. The enthalpy of formation for hydrogen gas is 0 kilojoules. And if you go to a table, for instance, your table in Chapter 9 or Appendix G in your OpenStax textbook, you can find enthalpies of formation for a variety of compounds, both molecular and ionic compounds that are likely to participate in chemical reactions. Now, what can we do with this? Well, we can use these enthalpies of formation to find the overall enthalpy change for a reaction without doing kind of all the Hess's Law mechanics that we previously did. We're using the same idea behind Hess's Law, but this is a more streamlined version. For a generic chemical reaction where we have A moles of A reacting with B moles of B to make C moles of C and D moles of D, delta H naught reaction is equal to the heats of formation of the products minus the heats of formation of the reactants. And so what we would do to figure out the enthalpy change for this reaction is we would go to Appendix G in the OpenStax textbook or the information page on the Sapling Learning website, and we would look for a table of delta H naught F values. And we'd say, okay, delta H naught F for compound C is this number. Delta H naught F for compound D is this number. If I take the stoichiometric coefficient, C moles of C times delta H naught F for compound C, and D moles of D for delta H naught F for compound D, I know essentially the enthalpy value that describes my products. The enthalpy value for the enthalpy change for the reaction is going to be the difference in enthalpy between my products and my reactants. So to figure out the enthalpy for my reactants, I take the enthalpy of formation for compound A, the enthalpy of formation for compound B, both of which we can get from the table, and multiply each by their stoichiometric coefficient. I calculate this for the products, I calculate that for the reactants, I subtract the two, and I get the overall enthalpy change for the chemical reaction. This is going to turn out to be a really simple and streamlined way to calculate enthalpy changes under standard state conditions for almost any chemical reaction you might be interested in. However, you have to do all the little things right. You have to find the enthalpy of formation for the compounds you're interested in and make sure that they are indeed in the correct phase. You have to remember to multiply the enthalpies of formation times the stoichiometric coefficient from the balanced chemical reaction. You have to remember that the delta H naught for the reaction is enthalpy of the products minus enthalpy of the reactants, not the other way around. So lots of little things that you have to line up correctly in order to get the correct answer when you're predicting an enthalpy change for an unknown equation. Come back in a minute. We're going to go through several examples where I talk you through the process of how we take enthalpies of formations for products and reactants and use them to find the overall enthalpy change for a chemical reaction.